moving on. The next topic is about quantum computers today and tomorrow. Quantum computers at the cutting edge of technology promises transformative breakthroughs. Today's prototypes hint at their potential to revolutionize computation. Tomorrow, as quantum capabilities mature, we anticipate advancements in diverse fields, from medicine to AI. Despite challenges, quantum computing stands poised to reshape our understanding of what's computationally possible. Our speaker is an associate professor in the Department of Condensed Matter Physics and Material Sciences at the Tata Institute of Fundamental Research, Mumbai. He currently heads the Quantum Measurement and Control Laboratory, where the main goal is to understand and improve the basic elements that go into building a quantum computer using superconducting circuit technology. Please put your hands together, ladies and gentlemen, as I invite Dr. R Vijayaraghavan, Professor at Department of Condensed Matter Physics and Material Sciences, TIFR, on stage, please. So, this is the. Yeah.
Oh, it's the one. Okay.
You can see your timer.
Great. My microphone is
On this. Oh,
hello. Am I audible?
yes.
Okay, great. Thank you for the kind invitation and introduction. Pleasure to be here. Very different audience for me to be giving a talk.
Hello.
So hopefully, I will try and make sense to all of you. Um, so I'm going to try and tell you a little bit about what quantum computers are, what they're capable of, and where we are in this short 15-minute talk. Um, but before we get into the quantum world, just want you to remind, all of this forum is about technology which is based on very robust and successful technology, which we now call classical computing, just because we have a new word for quantum. But this is the conventional digital technology. We know that information is stored and processed in the form of bits in different physical forms, depending on the storage medium or inside your computer. And this technology, of course, is extremely powerful and highly successful. I mean, the last 50 to 60 years have been amazing, and AI has now taken this to a different level. But you might be surprised to learn that there are actually certain kinds of things which this technology cannot do, and maybe will never be able to do it if we keep the technology in the same way. Look at this picture of a molecule. Okay, this is a very common medicine called aspirin. I think many people here might be taking it regularly. I certainly do. And it's not a very complicated molecule. It only has about 9 plus 8 plus about 20 odd atoms in it. And you would think that such a simple molecule, something which we take regularly, will be very well understood in terms of its fundamentals. Turns out that that's not the case. If you really want to understand the true physics behind how these atoms are interacting, if you want to model it exactly, and that's where the principles of quantum mechanics comes in, it turns out to do this on our conventional computer, even the most powerful computers on the earth, you cannot do a good job. The problem becomes so complicated so quickly the moment the number of atoms in these molecules becomes more than a few, that you are not able to do it. So of course, scientists have developed approximate methods to solve them, but you cannot solve this problem for even a simple molecule like this. Okay. There are other examples of problems like that. For example, the factoring problem, where you have these big numbers and you want to break them into factors. So this, what I've shown here, is of course a very simple one, and a simple computer program can solve it. But as these numbers become bigger and bigger, it becomes impossible to solve in using even the most powerful computers. And even something like the traveling salesman problem, where you have to find the best route. These are problems which becomes very complicated, and they are also very relevant for many areas as well. Okay, so this is where you need something new that comes in, and that comes in from the world of quantum mechanics. And the essential idea is that there are now new rules of the game. Okay, most of you might have heard about quantum mechanics, maybe in high school in chemistry, where you learn about the atomic model, that there is the nucleus in the center and electrons are going around in these orbits. a more accurate description actually says that, well, they are not really like planets going around the sun. It's a little bit more complicated. So don't worry about it too much, but there is this idea that these electrons sort of exist in clouds of probability. You cannot really pinpoint the location, but you can definitely say that it is in a lower energy state or a higher energy state. Okay, and these are quantum states. They are governed by a certain equation called the Schrodinger's equation, which now introduces some new rules which are present initially not there. Okay, and these new rules is what allows you to do things. So the idea in quantum computing is that you want to use quantum states. What is a quantum state here referring to? Is the electron in a lower energy state or a higher energy state? That is a quantum state. Okay, and the new idea is that these equations of quantum mechanics allow the electron to exist in both the energy states at the same time. This idea is called quantum superposition. And this is where usually the mind goes a little bit crazy. What does it mean? We can't understand it using our experience of daily life because there is no analog of that in our daily life. Okay, so you have to have a leap of faith here, but this is exactly how nature seems to behave. And when you do that and you use this quantum states to now replace your bits, so instead of 0 and 1, you have quantum state 0 and quantum state 1, you can actually put the system in a combination of these states, something like 0 plus 1. Okay, stop worrying about what it means. Just trust me that you can do this in a real physical system. You can also create something called 0 minus 1. Okay, this also plays an important role. And this is where we tend to say in a sort of loose language that a quantum bit can exist in both 0 and 1 at the same time. Okay, that's what the superposition said. In fact, these are not the only possibilities. You can actually imagine that the possibilities are infinite. Imagine the Earth and all the points on the surface of the Earth are actually valid superpositions. They are different combinations of zeros and one, where the North Pole and the South Pole are the original classical bits of 0 and 1, and all other combinations are allowed, and there are infinite possibilities. And it is this very simple difference that gives rise to new rules of the game. Okay, now if we extend this idea that you had one qubit which can be in 0 and 1 at the same time, if you now have n classical bits in a regular computer, you have 2 to the n possible states, and you can only be in one of them. But if you have a quantum system with n qubits, you can actually create a system where all the states are present at the same time. And this number 2 to the n can become very large very quickly. Okay, and then the purpose, or what happens in a quantum computer, is that the algorithm actually operates on this gigantic number of states all at the same time. The difference is, in a classical case, the conventional digital computer, you can only do it one at a time, whereas in a quantum computer, it can operate on all of them at the same time. Okay, but there is a caveat here that this exponentially large Hilbert space, which is what we call this set of states, exists. But when you measure, you only get n bits of information. Okay, this is another curious feature, that even though you can put it in all these different states, when you measure and ask electron which energy are you in, you only get 0 or 1. So you have to do something very clever and strange, and this is non-intuitive. You have to use this parallelism and interference. These are like waves. So, I'm showing this picture of water waves interfering. You have to interfere in some very hand-wavy sense. A quantum algorithm slowly cancels out all the wrong answers and amplifies the correct answer, and the correct answer emerges. Writing such an algorithm is non-trivial. Okay, so the problem, however, is that these qubits are not stable. This is sort of the current situation. When you prepare these systems, they actually change. They change in typically two different ways. I put the system in state 1. After some time, it comes back to state 0. This would be terrible. I sent my talk slides yesterday to NASCOM. I opened them today. If everything was 0, I would not be able to make this presentation, right? Hard drives can store data for years, but quantum bits can only store data for microseconds to milliseconds to seconds of time. This is the reality of the technology today, and this is inherent to most quantum systems. Another thing that can happen is that, remember, I told you that you can put this point anywhere on the globe. Where it's pointing exactly matters. As another kind of process can cause where it's pointing to change randomly over time, and that is also a problem. And these two things really are your enemies for running a quantum algorithm where you're trying to push the system towards the correct answer, and these random processes actually destroy the answer. And this is the reality of all machines which exist today. You only have a finite amount of time where you can make this work. So what's the solution? Is really the end of the story. Thankfully, there is something called quantum error correction. I'm not going to discuss this, but it turns out that it's possible to take many such bad qubits and create a perfect qubit out of that. And it is still not achieved. It's a very important milestone ahead, but a lot of proof of principle demonstrations show that this idea actually works quite well. Okay, so how to build these? There are actually many different ways of doing that. You can actually use atoms themselves. That's one popular approach, or you can use electrons as well as qubits. And the field I work in is to actually use something called a superconducting circuit, and they can also be used to build these quantum systems. There are many others as well, like you can use light itself, cold atoms. And currently, these three are the most sort of leading platform along with photons or particles of light. But we still have to figure out which one is going to turn into a practical technology in the future. Okay, so what some examples of what this quantum computer can do? Remember, I showed this problem. You can multiply two numbers, find the answer. It's very easy. The reverse problem gets harder and harder as the number becomes bigger. In fact, this is the basis of something called RSA encryption. All of your secure communications on the internet or credit card transactions use this RSA encryption, which relies on the fact that this reverse problem is very hard. In 1996 or 94, Peter Shor invented an algorithm assuming a quantum machine will be built, which uses these new rules, and basically he was able to show that this problem is now solvable. So you have these crazy numbers like 1,000-digit thing would take 10 to the 24 years on a conventional computer, can be done in tens of seconds on a quantum computer. And this has security implications as well, right? You have the problem of what is called unsorted searching. There is a 7 of hearts somewhere in these cards. You want to find it. How do you do it? Well, you just have to look at one of them. So on an average, you'll have to look at least half of the cards. The quantum version of this problem, you can put all the cards as sort of a combination, and the algorithm slowly amplifies the correct one. And it turns out that it does better than looking at half the number. You only need square root of the card number to solve this. And as the numbers of cards becomes bigger and bigger, you get improvement in the amount of time it takes to solve the problem. Okay. Many other things are also possible. Ultimately, the quantum computer allows you to model quantum mechanics, which is at the heart of all physics, chemistry, and biology as well. So you can simulate chemical reactions much more efficiently. It can be useful in drug design. You can invent new materials, say, for example, more efficient batteries, and also to do cutting-edge physics research. But there are many other kinds of problems which are also amenable for these kind of solutions, which includes logistic, finance, routing, and many more which are yet to be discovered. And that's really the thing. So in the last few minutes, I just want to quickly say, well, what's happening in India and what needs to be done. On the hardware side, I'm sure you're all aware of Google and IBM sort of leading the race around the world. Within the country, this activity is mostly limited to academia and it's small in scale. Okay, we have to scale up the resources, particularly with high-end, a lot of funds and resources. We need good fabrication facilities, high-end electronics to be able to build these systems together. There's a lot of engineering tasks that have to be done. So this is not always suited in an academic setting. So we need to really get industry with strong collaborations with academia and government resources to do this right. And a lot of breakthroughs are actually needed to make this technology practical. And those have yet to be made. And there is no reason why it cannot happen here in India if we take the right steps. Okay. There is also the aspect of algorithm development. Developing these quantum algorithms, I showed you this picture. It's highly non-intuitive. You have to have this quantum intuition, which is not so easy to do. And most new algorithms are sort of variants of those two examples I gave you, Shor's and Brover's algorithm. And you really need to increase the scale of operations currently in India, both in academia and industry. There's very little going on, and you have to scale this up if you want to develop new groundbreaking algorithms which exploit this. And for that, the human resource development is going to be very, very critical. Okay, and again, a strong collaboration is going to be needed. And finally, application development, which is actually to finding solutions. This is probably, using existing packages, this is probably the one which has the lowest barrier to entry because you have access to easier access to resources and it's easier to train as well. And it's possible to do this at scale. So maybe this is a place where we can actually start off doing a lot better in the near term. But the main challenge is that the hardware is still error prone. So even if you make an application to make a commercial case for somebody to adopt it, it's still hard because the hardware is not just there, but a lot of improvements are happening. And I think this will change very soon in the coming future. Okay. So before I stop, very quickly, we are working at CIFR in collaboration with DRDO and TCS, India's sort of first small scale quantum computer. This is a project going on, which is use some of our own ideas on the design. It's a technology demonstration project. It's not going to be very powerful, but the idea is to put together all the necessary bits and pieces. And this is being done in collaboration with DRDO for the hardware, and the cloud interface is being developed by the help of TCS. Okay, so to end, I just want to say a few recommendations here that I think industry should consider hardware development in a serious way with a very strong linkage with academia and use of government resources. Usually in India, we have not focused on hardware development, but this is an opportunity. I think we can also take the help of industry to develop technology for supporting development of quantum computers, and a very close collaboration to identify the kind of problems, maybe even more relevant to the Indian context as well. And there's going to be this national quantum mission, which is the government has announced. It will train a lot of people, and the industry should be closely involved in both the training and also to provide jobs to them once they come out of this. Okay, and be careful of the hype. Talk to academic experts to really understand what's happening around the world. So I just stop by saying that the quantum future is coming and we need to be ready. Thank you.
Thank you, sir. If you have any questions, okay, we take one.
Yeah, we can hear you.
Thanks for such a wonderful lecture on this topic. Actually, my question is on the national level. Like we know that means on yearly basis we have the 500 listing of computers, supercomputers. Okay, and if we can see the performance as a India in that, most of the time we have only 4 to 5 computers in that list. So if we reach all the milestone, if we can break through all the conditions like all hardware cases and all the things, if we can consider, so what is your opinion, can we crack on that list, like we will be the on the topmost of the that list, like as India, means what you think, if suppose that we crack the quantum technology, so we'll be on the top, like in the list of supercomputers.
Okay, so strictly speaking, supercomputers are a different technology. They use the current modality. Quantum
Yeah, but
computers will also be some kind of a supercomputer. They will also work in the same model of a central machine which is accessed remotely. Uh, Whether we can be a top player in this game, I think yes. I mean, we may not be the only player in the game.
yeah, because
Now because we are already starting a little bit late, but I think compared to other areas, we are not that late. And I think there are critical breakthroughs which are needed. And if those can happen, then we have some control over where this technology goes. But we have to do the right things. Apart from the money, which now the government is promising, we have to do all the planning and organization and make sure all the right players are included. So I feel optimistic about this, that we have a great opportunity to actually do this right this time.
okay, thank you for your answer.
I'm so sorry, but we'll have to take this question during the tea break, which will happen very soon. So thank you so much, sir, for an insightful session. If I can request you to kindly take center stage. And may I request Ms. Amita from NASCOM to kindly step on stage and give away the token of gratitude.
Thank you so much.